Okay, composite and inverse functions is what we're going to talk about today. Composite functions, or the composition of functions, is given by what looks like an O or a 0, but it's actually just an open circle. It's read f of g. So f of g, where we're going to take our function g of x and plug it in for every x in our function f of x. So the domain of the composition function f of g is a set of all x in the domain of g such that g of x is in the domain of x. So basically, as long as one is not making the other undefined, you're good to go. So we're going to jump right in by finding compositions. So in number 1, f of x is 2x plus 3, g of x is x minus 6. So the first thing we're going to do is we're going to find f of g. So we're going to take g and we're going to plug it in for every x in f. And we're just simplifying. So we're going to distribute the 2 and then combine like terms, which gives us 2x minus 9. For b, to find g of f, we're doing the same thing, but we are going to take our f of x function and plug it in for x in our g of x function. So we're going to take that 2x plus 3, plug it in for x, and just combine our like terms. So we end up with 2x minus 3. And then when we look at f of g of 4, you got two options. You could plug 4 into g of x and then take that number that you get and plug it in for x. But really, this is like saying f of g of 4. So we already know what f of g of x is. So we could just plug that into what we got in part A and call it a day. If you didn't want to do that, you could just plug in 4 for x in g of x and simplify it down. So this is your g of x function here. So we would plug in 4. So 4 minus 6 is negative 2. 2 times negative 2 is negative 4. Plus 3 is negative 1. Or if you wanted to go and plug it into what you had for f of g of x already and use this, 2 times 4 minus 9, 2 times 4 is 8, minus 9 is negative 1. So it's the same thing either way. I would encourage you guys to try number 2 on your own. You're doing the same thing. Just plugging them into the x and the other function and simplifying it down, and then coming back and comparing what you got to what I got. So for f of g of x, we're going to take this x plus 2 and plug it in for x in f of x. So x plus 2 squared plus 3. Remember, you have to FOIL this, which would become x squared plus 4x plus 4 plus that 3, and then combine your like terms. So in part B, we're doing the same thing, but we're doing g of f of x. So we're going to reverse that, and we're going to take f of x and plug it in for x and g of x. So x squared plus 3 plus 2 is going to give us x squared plus 5. And then for part C, g of f of negative 3 we're going to plug in -3 for into f of x, and then plug that into g of x. So -3 squared is 9, plus 3 is 12, plus 2 is 14. So in number 3, we're going to find f of g of x and g of f of x, and then we're going to state the domain. So if we start f of g of x, we're going to plug in g of x in for f of x. And we're just combining like terms. So we end up with the square root of x minus 2. And when we look at finding the domain, we can't have a negative value in our square root. So we need to know what's going to make that 0. So x minus 2 equals 0 is going to make x equal 2 if we solve that. So we want any value greater than or equal to 2 for that domain. And then for g of f of x, we're going to plug in f of x in for x in g, which we can't simplify anymore. We still can't have a negative in that square root, so we're going to need the x value to be greater than or equal to -2, because that -2 is what's going to make that equal to 0. Okay, so by interchanging the first and second coordinates of each of the ordered pairs in a graph, you can form another function that's called the inverse function. So if the function f has an inverse, it's denoted f negative to the -1. It's important to remember that this -1 isn't an exponent. But it's just a way to denote an inverse. So a function f is 1 to 1 when each value of the dependent variable corresponds to exactly one value of the independent variable. So we use what's called a horizontal line test to test for inverse functions, because if function f has an inverse, if and only if it's a 1-to-1 function. Graphically, a function f has an inverse function if and only if no horizontal line intersects the graph of f at more than one point. So 1-to-1 is kind of the opposite of a regular function test. In 1-to-1, our x's can repeat, but our y's cannot repeat. So it's kind of the reverse of that. So when we have the same y value, it is not going to be 1-to-1. So in 4 and 5, we're going to sketch the graphs of each function and then do a horizontal line test to determine if it's going to have an inverse function or if it's 1-to-1. So you can make a table if you want, or you can just sketch based off of what you know about those types of graphs. Either is fine. So for number 4, if we make a table, -2 squared is 4, minus 2 is 2, -1 squared is 1, minus 2 is -1, 0 squared is 0, minus 2 is -2, 1 squared minus 2 is -1, 2 squared minus 2 is 2. So -2, 2, -1, -1, 0, -2, 1, -1, and 2, 2. So we have our quadratic, and if we do a horizontal line test, that horizontal line crosses the graph at more than one place, so it will not have an inverse function. Same thing for number 5. So if we graph our function, we're going to start down at -1. Our slope is 3, so up 3 over 1. If we draw horizontal lines, there is not a horizontal line that we could draw that would intersect this graph more than once. So this one will have a inverse function. A function f has an inverse function if we do the composition of the function and the inverse and we get x, and then we do the composition of the inverse and the function and get x as well. So if you do both compositions and they're both equal to x, then it's going to be an inverse function. To find an inverse function, you're going to take your equation for f of x and you're going to replace f of x with y. You're going to then switch x and y in the equation and solve the equation for y. If you're asked to verify, you'll verify that they're inverses of each other by showing the two compositions both equal x. So in 6 and 7, we're just finding inverse functions. So we're going to change the f of x to y. We're going to switch x and y. And we're going to solve for y. So I'm going to add my 7 to both sides. And then I'm going to divide both sides by 5. And then we tend to always want to make sure we rewrite it in that function notation. So inverse of f is going to equal x plus 7 over 5. Same thing with number 7. We're going to replace g of x with y. And then we're going to switch x and y and solve for y. So first thing I'm going to do is I'm going to divide by 3. And then to get rid of y cubed, I'm going to take the cubed root. And then I'm going to write it in that function notation. So in 8 and 9, we're just showing that our two functions are inverses of each other by showing that they're reflections. So inverses reflect over the line y equals x, which is the main diagonal in your graph. And the ordered pairs of your equations are just always reversed. So if I graph f of x, I'm going to start at 4. And I'm either going to go up 1 over 1 or down 1, left 1. Either's fine. And connect my points. And then for g of x, I start down at -4, up 1 over 1. And connect my points. So they're going to reflect over that line y equals x. And when they reflect over that, their ordered pairs just swap. So this 0, 4 becomes 4, 0, which we have here. This 1, 5 would become 5, 1, which we would have right here. -1, 3 would become 3, negative 1, which we have here. So all of those ordered pairs are just flip-flopping and they're on the opposite line. So same thing with number 9. So if I graph f of x, we want x to be greater than or equal to 0. So if I plug in 0, I'm going to be at negative 1. If I plug in 1, I'm going to be at 0. If I plug in 2, I'm going to be at 3, and so on. And then if I graph g of x, if I plug in negative 1 for x, I get 0. If I plug in 1 for x, if I plug in 0 for x, I get 1. And then if I were to plug in 3 for x, I would get 2, and so on. You could plug in values that would give you decimal answers, but that just makes it harder to graph. So if I compare those ordered pairs, they're just opposites of each other. So the x and y just flip-flop. 2, 3 becomes 3, 2, 0, 1, 1, 0, negative 1, 0, 0, negative 1. If you have questions on any of this, let me know. Shoot me an email, get on Google Meet. Don't forget to do your homework.